Hello and welcome to this video. In this video, we will learn about threaded binary trees. Now, if you remember our last video, which was about binary tree, then you will remember that there are nodes which may have null pointers. For example, leaf nodes have two null pointers, and suppose there is a node which has right child but no left child, then that leaves a null pointer. And the other case also is true when the node has left subtree but no right child. So in that case, that will be a null pointer. So what we do in threaded binary tree is there are two types. One is single threaded. In this case, the null right pointers point to the in-order successor. That is, if the successor exists. And the other variation of this is double threaded. In this case, left pointer points to in-order predecessor and the right null pointer points to in-order successor. There are certain advantages of this kind of modification to binary search trees. One of the advantages is that it makes linear traversal of elements possible. The second advantage is that we don't need stack anymore for this linear traversal. Third advantage is that this new structure makes it possible to find parent node without explicit use of parent pointer. Backward and forward traversal of nodes is possible in an in-order way. Searching is easier because you can find in-order predecessor and successor. Finding predecessor and successor nodes of any node is fast. Nodes. Okay. Now the disadvantage is that because now we have to keep information about the successor and predecessor, the memory requirement needed is heavier. Insertion and deletions become more complex simply because now we have to manage those extra links. Therefore, it becomes more time consuming. And this structure is less flexible compared to binary search trees. For example, rotation and all will become very complicated in this. That is, if you want to balance the tree, it will be far more involving. Applications of threaded binary trees are expression evaluation. For example, postfix, infix, that kind of evaluation. Database indexing. Well, databases use a different kind of trees, typically SQL databases. They use B plus tree, the classical MySQL or PostgreSQL or Oracle databases use B plus trees, which is a disk-based data structure, which I have mentioned in the fourth point. But threaded binary tree can also be used, just that B plus trees are better. New kind of databases, for example, CockroachDB, they make use of something called log structure merge tree to manage the database structure and so on. Another uses can be symbol table management of the compiler. That is, when a compiler makes the symbol table of a program, that management can be done by using a threaded binary tree. Now, as always, we have divided the program in three parts. This is the main.c file, which is the main driver file. We insert values like 40, then left side 20, then right side 60, then 10, which would be on left of 20, then 30, which will be on right of 20, 50, which will be left of 60, and 70, which will be right of 70, and 8, which will go left of 10. Then we do an in-order traversal, delete one node, and then we do in-order traversal again. This exit success macro comes from stdlib.h. It includes our header file of threaded binary tree.h. We include three standard libraries: stdi.h, stdlib.h, and stdbool.h. The structure has two pointers, left and right. Point to left and right node. We have a data, which can be anything. can be a char pointer, it can be a float, it can be a structure, it can be a string, it can be anything. Now we have two booleans, lthread and rthread. So when I say that a leaf node, or rather null left and right pointers point to the predecessor and successor, we don't create a pointer actually. The boolean value indicates whether it actually has a predecessor or successor or not. That is, it indicates whether a left child or right child exists or not. It is not embedded into the pointer kind of structure. We have three standard functions: insert, delete, and in order traversal. Now we go to the core program's logic. If you have followed my binary search tree, or you know binary search tree, how it works, it is very easy to understand how the insertion will work. So we receive the root node and the data. We make our node as root. So assume that in the beginning there is no element. So node root will become node, okay, and parent will be null. Now in this case, the node will be null because our root is null. We are inserting our first element. So nothing happens in while loop. The allocation will happen, memory allocation will happen for the node, and data will be assigned. Left thread and right thread will be set to true. That is, both these will point to predecessor and successor, which do not exist yet. Right? We see parent is null. So root will become temp. Root will be assigned temp. Left and right will be set to null. These won't come in picture. So if you remember from main.c, 40 will be inserted. All right. Now we insert 20. In this case, we will receive root as 40. Now node is not null. We check if data is equal to node's data. Okay. That is not true. 40 is not equal to 20. So we set parent as node, which is essentially root. So parent is now node. Now data will be compared with the node data. So 20 is less than 40. This will come in picture. Now it will check if node lthread is false or not. Okay. Now if you follow this logic, what is our node? Node is nothing but root. Okay. So you see root has been given here. So root lthread in previous one which we have inserted is set to true here. Alright. So this is not false. Alright. So this will not happen and break will happen. So essentially in this entire thing, what has happened is root has become the parent node. Now memory allocation will happen, and then this will be set, and then root will become the new temp, left right will be set. So still root and the new node 40 and 20 are not connected. So in this case, now we see what will happen. Temp's left will become parent's left. So parent's left will be assigned here, and temp's right will now point to parent, and lthread will be set to false, parent's lthread. So root's left child now exists. Okay, and root's left is temporary, and parent's right. Now you see what is happening here. Temp's right will become parent. That is, the right null pointer of temp will now point to parent. Is the 40. 20 is right will point to 40, and 20 is left will point to parent's left, but there is no parent's left. I mean, it will point to itself in this case. Okay, because parent's left is 40's left is 20, and 20's left is pointing to itself. Okay, so that's why R thread is not set to false. All right, L thread is set to false because the left pointer will point to the predecessor. There is no successor in this case. Hang on. I mean to say the successor exists in this case. Okay. The predecessor does not. So right will be set true. Left will not be. Okay. So this is how the insertion routine will work. Now we look at in order traversal. So to traverse in an in order fashion, what we do is we take root and assign it to node. First we check whether left side is false or not. As long as left side is false, traverse to node. So suppose there is an element here, there is a left child, there is a left child, so we go on traversing. Once the L thread is no longer false, what will happen is we have arrived at the leftmost element. Now if the node is not null, because this can be null, okay, you reach a node and its left could be null. Okay, node is not null, we print the data, and then we find the in-order successor. Now in-order successor we find here. How you find in-order successor is that if R thread is set, then you find the node right. You go to the right side of the element, okay, because left is no longer there. This is the leftmost node, okay, so no longer left child is there, so we go to the right side. Now we set node to node right. Now it returns here. So if there is a right node is there, if right node is not there, then node right is returned, and this loop will terminate because the next node will be null. But if that is not the case, if our thread is false, okay, then this will not happen. Now we go to the right side. Once you go to the right side, again you try to go all the way to left, and once you reach the leftmost child of the right subtree, you return it. That would be the in-order successor of this node. Okay, so that's how this in-order traversal works. Now we come to deletion. Okay, now deletion. For deletion, first what we do is first we have to find whether the node exists or not, the data is there or not. Okay, so for example, we do deletion of root and 20. So this is the method. So in this case, data is passed. So first our task is to find the data. So if node is not null and data is equal to node's data, then we take the loop. Remember that root is assigned to node. That is not the case. We make the parent equal to node. Okay, and if node is if the data is less than node, then we go to left subtree, and as long as L thread is false, we keep going on to left. Okay, if the data is greater than node data, then we go to the right side. Okay, we do this till we get the data. If it is not there, then this found will not become true. Remember that found is initialized to false. Now if found is false after this, then the data is not present. I think a better code would be to return from here. So we are returning node pointer. We can return null here. And okay, so if we return null, this should be ignored. Okay, if you, there will be complications here if actually let it be there. Don't return null here. There will be complications because of this. Okay. Now we come to other cases. Okay, now suppose found is true, then there can be a case that this particular node which is to be deleted has both the children, left node and right node both are there. Okay, so we call delete both children. Other case would be that left child exists, but right child does not. Then we call delete one child. The other case could be that earth side is false. That is, the right child exists, but the left is not. So we call delete one child. The final case could be that there are no children. In this case, we call delete no child. So first we see delete no child because that is the simplest. So delete no child. All right. So in this case, the node which is to be deleted does not have any children. Okay. So what we do is, if parent is null, okay, then it is essentially root node. So we set roots to be null. Okay. And then we free the node, we return. Now suppose that tree has two elements, that is the root node and the left node. 40 and 20 are there. So in this case, and suppose the data entered is 20. So in this case, if the node is equal to parent left, so parent would be root and node would be 20. So node is parent's left in this case. So we will set else thread to be true of the parent, okay, because we are going to delete it. And then we set parent's left to node's left, which is null in this case, or rather it would be itself, which will become null. Okay. So once we do that, we free the node and we return the root. But if the left child is not there, there is a right child, we set the R thread to true and we set the parent's right to node's right. Why this is done, you will see, because when there are larger nodes, it will become complicated. That is delete one child, delete no child. Now suppose that we are deleting one child. Okay. All right. Now let me revisit insert a bit. There is something wrong here. So let's revisit a bit here. So we insert 40. So in this case, parent is null. Left and right both become null and we return root. Then we want to insert 20. Then temp, else thread and R thread are set to true. Okay. And then data is less than parent's data. Temp's left would be parent's left. Okay. Now parent is set to root. Okay. Parent is set to root. So its left would be null. Okay. So that makes sense. Yeah, it should be null. So this will work nicely because parent's left will become null in this case. Now we come to delete one child. Suppose there is 40, there is 20, and then there is 10. Okay. And we want to delete 20. 40, 20, 10, and we want to delete 20. So that is our case. So root node is 40. So we check if node's else thread is false or not. In this case, there is child node. That child would be node's left. Okay. Now there is no right child in this case of 20. 40, 20, 10. So all are left child. So this case will not be it. We will go to child is equal to node left. Now if parent is equal to null, which is not true in this case, we have 40, 20, 10. Now node is equal to parent left. So the node is left of parent. It's true. 40 is of 20 is 40 is left. What we do is we set parents left, that is 40 is left, to the child, that is 10. We set 40 is left to 10. Okay. Once we do this, we find in order successor of the node. So 20's successor would be 40 and its predecessor would be 10. Okay. In order predecessor would be 10. Now let's look at in order predecessor function and in order successor function. Okay. Now you see in order successor, so our node is 20 and its R thread is false. Okay, so node write is not there. So we return node itself. So node R thread would be false. Yes. So node write cannot be in order successor. No, node write would be set to parent write in this case because data is greater here. So yeah, in this case, 40 would be returned as the in order successor. 20 in order successor would be 40. Once we have that 40 and in order predecessor in this case would be, if you see L thread is true, then node left is returned. So 20 is left would be 10. So this would be 10. So what we will have here is successor would be 40 and predecessor would be 10. So now we set nodes L thread to false and predecessor's write as successor. So what we do is predecessor is 10. Hence write should be 40. Okay, that will be set. So this is how we find the predecessor. Okay, but there is a left subtree, so this will happen. So that is how we find out. Let me once again go to the predecessor function. Hang on. So its left side would be false and predecessor would be 10. Predecessor is 10. It's a bit confusing here to explain without example. Let's go to the insert function carefully. Only then we can test. So suppose first we insert 40. Then we have 10 here. I should have made diagrams so that we would not have to go through this. So here we have 20 and then another flash here, and then we have so let's look at each of these. Now when 40 is inserted, this case is it. L thread is set to true, R thread is set to true. That's it. Thread and R thread set to true. Now in the second case, when 20 is inserted, L thread and R thread would be set to true. But in this case, data is less than parent data. So temp's left, its left will be parent's left. Okay, so parent's left is nothing but 20 itself. Okay, parent will be set to root here. Okay, parent will be set to, hang on. So let's revisit this. So 20 is to be inserted and root is 40. So node is not null and data is not equal to node data. Parent will be node. Parent will be 40 in this case, and data is less than node data. And L thread won't be false because L thread is set to true in previous case. So this is no longer true. Now the node is created. 20 is created. L thread and R thread is set to true. 40's R thread is still true. Okay. So we'll hit this case. 40's parent L thread is set to false. So L thread will be false. Parent's left will be temp. So parent's left will be 20. Okay. The only concern is this. Okay. Now this temp is this temp is parent's left. All right. But parent is root. So root's left is now temporary's left. Temporary's left. Okay. So in this case, left would be null. Now parent's left, if we set to null, okay, the parent's left is set to null. Fine, because we are going to overwrite this here in any case. All right, and temp's right is set to parent. The right will now point to 40. that is the in order successor. But in this case, predecessor is not set. Now when we insert 10, what will happen is first it will come here, parent will become node, that is 40. Then in the second iteration, in this iteration, else side will become false. When 40 is encountered, this will be false. So node will become 20. Once node becomes 20, data will be less than node, but 20's else thread is not set to false, it will be true. So we don't enter here and we fall in here. And then 10 will be initialized, and then same thing will happen to 10 also. 10 will be pointing to 20, in order successor. Okay, there is no predecessor in this case. So that's how you see in order and predecessor functions will work, and these will be set. So all you need to do is you create a diagram, run through all this, and it will all make sense. Okay, and similarly we perform this for delete both child. It just makes use of delete no child and delete one child. That's all it does. There is not much logic in this. Should be no. So now we are ready for a run of this program to see if it actually works. So for example, I will actually delete, so I have deleted this 20, which is in between. Let's try deleting one of the leaf nodes. Delete root, 8. And then again you do in order traversal of root. And then we try to delete again one of the right subtrees element. Say we delete 60. And then we again print in order root, and then we again delete one of the leaf nodes. Delete. So if we delete in this case, then we should try deleting 70. Okay, and then we again do traversal of root. Okay, so if this works, it works. Now we have already compiled the code, so I'll just recall it. Okay, the slash tokens have messed up. Okay. So we see we delete 20, or in order traversal is very well correct. Then we delete 8, that also works. And then we have deleted 60, that works. Then we have deleted 70, that works. Now one more test, what we can do is we can actually try to delete the root node itself. So let's comment out all this, and we delete the root node itself. So we delete the node 40 itself. That should show that it works. So you see, we have deleted 40 here. It does not come anymore. Let me zoom it a bit. Okay. So now you can see all the deletions in the picture. So the 40 is deleted, and then for 40, which one we deleted? We deleted 8, and then we deleted 60, and then we deleted 70. So yeah, this works. So I will, it is not very clear from what I have said, the functionality of this. What I will suggest you is to draw the diagrams and then try to execute the logic on pen and paper, and then it will all become clear. It is very difficult to explain this complex insertion and traversal without using graphics. I'm sorry that I have not made the graphics. So with this, we come to the end of threaded binary tree, and I hope that you have found this video useful and informative. So please subscribe to the channel, like and share the video, and make use of the comment box if you want to say anything. The reason for asking for subscription and like and shares is twofold. One is that it motivates me to make more such videos, and second is that it reaches more people like you. So please help your fellow programmers by sharing and liking this video, because the way YouTube works is that the more likes and shares and views are there, the more it comes into recommendations of others to watch. So I'm just asking for help a bit here. So I hope that you have enjoyed. Thanks a lot for watching. Happy programming.